For our purposes, a collision is an interaction in which two objects exert forces on each other with external impulses known to be zero or negligible. Eventually, we can extend this to any number of objects. This means that momentum is automatically conserved in collisions. Any collision can be classified as exactly one of the following types. They can be perfectly non-elastic, they can be non-elastic, they can be elastic, sometimes also called perfectly elastic, or they can be superelastic. We're going to approach these in a little bit out of order. For an elastic collision, kinetic energy is conserved. That's the definition of it. What's going on here is the objects exactly bounce off each other, but they don't change their final shape, so their internal potential energies can't change, so the kinetic energy also can't change. Right? Elastic is the easiest to understand, sort of. Turns out, we'll see later on, is a little computationally challenging, not too bad, but and it's the one students fall back on early on, even though it's a pretty strict condition that kinetic energy is conserved. The sort of polar opposite to that is the perfectly non-elastic case. In this case, the objects stick and move together, and they deform in some manner. They change their shape because that's the only way they can stick together. Otherwise, they would flex and then pop back to their original shape and push off for each other. So the only way they can stick is if they are somehow, on some level, rearranged. It could be something like a car crumpling into another car. It could be something like a hook and eye system, like for Velcro, where they move around and get hooked in there. But something has to change. And because of that, they lose kinetic energy. In fact, they lose the maximum possible loss of kinetic energy. There's the maximum they can possibly lose consistent with this momentum situation. And then the mixture between those two is called non-elastic, just generically non-elastic. Or sometimes called partially non-elastic or called partially elastic. But this mixture is where the objects deform, but they don't stick together. These tend to be pretty messy. These tend to be pretty ugly to work with. This is the case of like a car hitting another car and bouncing off, where they'll have some little bit of crumpling, but not 100%. So they'll neither have all their energy, nor they'll have lost all their energy, but some mixture between. Generally, to do these problems, you'd have to have some better specification of what the loss of energy is. In this case, some kinetic energy is always lost, but it's not the maximum amount that you can have. And there's even really a fourth case called superelastic, which is fancy, but it means the kinetic energy is more than conserved. It is added to the system. This might be where, if you imagine like the carts we have in lab, where there's that spring-loaded thing, it comes in and it pops the spring, and the spring pushes out. Generally, there has to be some source of energy within the system that is released to give you some extra kinetic energy. So it could be a broken bond in a chemical system, or it could be a spring, or some sort of internal combustion engine that goes on, or something that can yield extra energy into the system. Non-elastic collisions, particularly perfectly non-elastic collisions, are the easiest to deal with and the most common to come across, and is definitely the foundational thing for understanding all the others. The objects in non-elastic collisions stick together, or they try to, and that requires that they deform. They change shape in some fashion. This rearrangement of configuration changes their energy, which is why some energy is quote-unquote lost. As always, the energy is really still there, but it's become potential energy or heat or some such. In the special case of an object of mass m1 moving at velocity v1 initial, running into and sticking to an object of mass 2 moving at velocity v2 initial, we can find the output speed vf. This is a case it's a one-dimensional collision, and in this case it's completely specified. Given the initial the masses and the initial velocities, we can exactly say what the outcome velocity has to be. And we do it relatively simply. We have our little picture here saying something of m1 moving at v1i, crashes m2 moving at v2i, kablow, we don't know what happens during this, and the whole point is we don't know or care what happens. Various horrible forces go on, and they stick together, moving off of speed vf. Right? Then we can just say the initial momentum, which is m1 v1i plus m2 v2i, equals the final momentum, which is just their sum, because they're moving as one object, times vf. And then we can solve into this equation. Notice there's no freedom to choose vf. It's entirely specified by the initial velocities and the masses together. You have no options as to what comes out. If this is a totally non-elastic collision, there is only one possible output. Also, don't memorize this formula. It's pretty easy to derive, and knowing where it comes from can be very important. Alright, so let's look at a sample problem. A 50-gram cart hits and sticks to a 750-gram cart initially at rest. Immediately after the collision, the pair moves off at 2.35 meters per second. How fast in meters per second was the 50-gram cart moving before the collision? We see it solved here, where we have our little picture. And we see we have two of our masses and some initial velocity, and 0 velocity for M2, so of course that one drops out. And then they move together, so we just add their masses, and we can solve over and find that we get 37.6 meters per second. Not a particularly spectacular problem, but a good little warm-up. Sample problem 2, the so-called ballistic pendulum. This is a relatively common introductory physics problem, and one the committee likes to revisit from time to time, so it's worth understanding. The details might be different, but the basic idea is a 25-gram bullet is fired horizontally into a 1-kilogram wooden block suspended by a string of length 75 centimeters. The bullet becomes lodged in the block, and together they rise until the string makes an angle of 22 degrees to the vertical. Find the initial speed in meters per second of the bullet before collision. Here we want to basically take care of that there are really two things going on. The first thing is the bullet hits the block and gets stuck. That's a collision process. It happens very quickly. During that time, the bullet really can't, or the block can't really move very much because this is happening on sort of microsecond scales. And so it's basically just a totally inelastic collision. So we have our bullet about to run into our block. And then kablooey, something happens. And now we have the block, and the bullet is stuck inside of it, and they move off at some lower velocity. But after that happens, and the collision is done, which remember happens very, very quickly, so the block has not moved significantly. After that, the block is just a thing which is at the bottom of a string and has a given kick at the bottom, and it will swing up and come to rest, and that's probably most easily modeled as a energy problem. The thing goes up to some angle. My angle is certainly not 22 degrees, but that's not relevant for the picture. And in so doing, it is raised some height. And if we can take that height, we can turn it back into the initial velocity that it must have hit with. And the idea being, if we take this height and turn it into this initial velocity, well, that initial velocity is, of course, the same as this output velocity here. And given this output velocity, we can go back and get the initial velocity of the bullet. And that's what we're going to do on the next page. There's one minor complication, which is finding the actual height. So we have that the thing is of length L, and it swings up, so I should really have some sort of circular arc, to some height H. And what I want to indicate, of course, this length is still L. The length of the string was L the whole time. And this, of course, is also H. And this is L minus H. So we'd have something like L minus H. Well, L minus H plus H equals L. Duh. But this distance is also L cosine theta. Right, because we have, if we look over here, L and theta and the thing I want. So that will be L cosine theta. So we get something like H is L minus L cosine theta. Putting that all together, we have that we're going to start actually after the collision. We'll conserve energy. So we have the energy at the bottom equals the energy at the top. 1/2 the total mass times the velocity at the bottom squared is the total mass times GH. Of course, there's no potential energy. We'll set the 0 here. And there's no kinetic energy because it comes to rest. That's its greatest height. And therefore, the velocity at the bottom must be root 2 GH. But we found on the other page that H is 1 minus cosine theta. So we have the V at the bottom is root of 2 GL times 1 minus cos theta. All of it under the radical. And then during the collision, momentum is conserved, although energy is not. And so the initial momentum equals the final momentum. And we can kind of put that back together and find that the velocity of the bullet must have been 42.4 meters per second. This technique is actually how they generally measure muscle velocities of things in forensics cases. They fire them into known things. It's low tech, but pretty reliable way of calibrating your gun caliber. We can see this demoed in this very short video about how it fires. It's not that impressive a video, but the idea being we could figure out the height through which it moves or the greatest angle it comes out. It's more interesting if we see what the energy development is in that case. Here we have an infrared camera approach to it. It's a little annoying in the sense in that we're now looking down the barrel of the bullet of the can that it's being fired into rather than the side. But we can see that we have bright objects are also hot objects. These are places where there's real heat. And this is a relatively cool area. The gun is going to be coming towards the camera, or the bullet comes from, we can't see it, but it's behind the can here, coming towards the can, and we can see what happens. And you see a couple of things. You can see that the ball has a lot of heat because it's coming from the gun, and it also heats up the can a little bit. So that's what's seeing more time. See how the can is a little bit hotter, and we can see where the bullet that has come to rest inside the can is hot, but giving up its heat now to the can as it goes on. Alright, two identical carts traveling in opposite directions are shown just before they collide. The carts carry different loads, initially traveling at different speeds. The carts then stick together after the collision, and three physics students discussing the situation make the following contention. Alex says these carts will both be at rest after the collision since the initial momentum of the system is 0, and so the final momentum of the system has to be 0 as well. Belinda says if that were true, it would mean that they have 0 kinetic energy after collision, and that would violate conservation of energy. Since the right-hand cart has more kinetic energy, the combined carts will be moving slowly to the left after the collision. And Chano thinks that after the collision, the pair of carts will be traveling left, but at 20 centimeters per second. That way, conservation momentum and conservation energy are both satisfied. Which, if any, of these students do you think is correct? Here we're going to say that our correct answer is Alex. The momentum is clearly 160 going this way and 160 going the other way, so the initial momentum of the system is 0, even though things are moving. Notice how this is different than kinetic energy. In kinetic energy, if anything's moving, the kinetic energy has to be non-zero, if anything's moving. But since momentum is a vector quantity, it can be 0, even if it's the things that make it up are non-zero. The system momentum will be conserved, and so Alex is correct that the final momentum is 0, but now that they're stuck together, the only way to get the final momentum to be 0 is if their velocity is 0. Belinda is correct that this violates conservation of energy, but that's okay. We don't know anything about the forces that are causing these two things to stick together. We have no reason to think that they're conservative forces. In fact, we're pretty sure they're not. And so we lose a lot of our kinetic energy, probably to heat, a little bit to sound, maybe to light if it's a particularly spectacular collision. But we don't expect kinetic energy to be conserved in general. It's not a general rule. So there we go. And Chano is just off on so many levels. Alright, if the collision is in 2 dimensions, then the combined object moves off in the direction given by the vector sum of the initial momentums. But, and this is key, the momentum is conserved in each direction independently. So you can just get the components of the momentums and then make them all add up properly. So, in each case, draw a blue circle around the letters corresponding to the case with the greatest magnitude of the two-ball system, and a red circle around the letters with the least magnitude of the two-ball system. Probably easiest if we just compute them. We have to notice that, for instance, in part A, this has a momentum of 6 going that way and momentum of 8 going that way, but if it's 6 over and 8 up, it's actually a total momentum of 10. And likewise, here we have 8 downward and 6 over, so that's also going to be 10. In case C, we have 8 moving straight downward, but we have 8 moving straight upward. This is a total of 0. And here we have 6 going rightward and 9 going leftward, so that's a 3 going leftward. So we can see that before they collide, the system momentum is largest in A and B, and 0 in C, which is the least. Now, we want to know what happens after they collide if they stick together. Again, draw blue around the greatest magnitude of momentum of the system and red around the least. But this is, of course, a trick question because during this process, the momentum is conserved. So whatever the two-ball system momentum was beforehand is the same after. So they're going to be the same. And actually, it doesn't matter whether they stick together or they bounce elastically. The momentum is conserved.